Welcome. This is the Hyperbola numerical exercise video. We did videos on the theory, and I don't know about you, but when I was in school, I'd rather see an example worked out, and the theory, I understood it later in the context. So that's the idea. So this is two examples where I give you, as you can see, an, an expression, an equation, and the instructions are analyze and graph. So analyze basically is a catchphrase for say whatever you can about it. You know, get it standard form, show all the steps, find the center, find the vertices, asymptotes, whatever is involved. That's what that means, and then draw a reasonable picture. Now, on the hyperbola problem set take home, I'm going to provide you with an empty grid. It's hopefully designed to um, work out well. In other words, the numbers are supposed to work out. I've already done them, but the problem is sometimes I make mistakes. So, but it should work out nicely. Okay, so here we go. First off, you got x squareds and you got y squared. So it's not a parabola. A parabola only has one of the terms squared. Secondly, since it's a takeaway in between the terms and not a plus, as you can see, it's not an ellipse. And thirdly, since they have the coefficients of 4 and a 1, they are different, so it's certainly not a circle. So when you see this kind of pattern, typically you would expect an hyperbola. Okay, so with that in mind, and with most of these in mind, what you want to do is you want to get these terms in some order. I'm calling that rearranging terms, and generally completing the square. So that's basically the process. Now I indicated here this is a type 2 hyperbola, which means it's going to be, I don't know, higher than it is wide, I guess. Okay, um, we don't really know that yet, so but that will become clear later. Okay, so you got y squared, you got the minus 2y, and then you got your x squared terms, your x terms, the 4x squared and 16x, and the 19 we know enough, we get pushed over on the other side. So one thing you have to be careful about with a hyperbola is you have this takeaway going on. So be very careful. If I think of this as multiplying by a negative 1 and I push it through, you can see negative 4x squared is correct. And you can also see negative 1 times this gives you a negative 16x. So you have to be very careful of the sign right here. So just be careful. And the way you tell, of course, is you multiply back in your mind and you just look at it and say, yeah, that's the way it's supposed to be. Okay, so now it's the idea is completing the square. So you get a 1 here, and here you got to factor out the 4, and half of this guy, half of the coefficient's 2, 2 squared is 4. So what's happening here is you're adding 1 to the left side, you got to add a 1 to the right side. Don't forget, an equation is a balance. And over here, since this is negative 4 times 4, you're really adding a negative 16 on the left side. So we do the same thing. We add a negative 16 or subtract the 16 on the right side. Okay, so the right side bubbles down to a 4 and the left side looks like this, and then experience. And you know, a lot of things in life come down to experience. Experience is knowing that standard form means this has to be a 1. So the way I accomplish that is I divide each of the terms by 4, and this now is my standard form. Okay? Okay, so working from here, we're supposed to know with a hyperbola, the a squared goes with the positive term. So 4 is your a squared, and the b squared goes with the negative part. So that would be 1. So a is 2, b is 1. Also, when it's in this form, you should be able to tell the center. So x first before y, of course. So you have negative 2, 1. So h is negative 2 because it's usually x minus h quantity squared. Y is, and k is a 1. So here's your center. So immediately, you may want to plot that point, negative 2, 1. And knowing that it's the up-down type, we call type 2. We're going to count up 2 units and down 2 units from the center to get our vertices. All right, so up 2 units would give us a vertex. I'm labeling it vertex 1, but that doesn't really matter. Would be negative 2, 3. And counting down 2 from the center, I get negative 2, negative 1. So that's how I get my vertices, just counting boxes. Now, in an hyperbola, not an ellipse. An ellipse, you got a squared equals b squared plus c squared, but in a hyperbola, and you go back to the derivation, you can see that a squared plus b squared is c squared, so putting in the numbers, we get c is radical 5. So c is going to give us the location of the focus, or the foci, and we basically count, in this case, up and down from the center. So radical 5 is about 2.236, so roughly we're going up 2 1/4, it's going to be there, and counting down 2 1/4, the focus will be there. And then you're expected to be able to get the coordinates. So since the x value of the foci, because it's a type 2, have the same x value as the transverse axis, right? So your x value is a negative 2 and the y value is 1 plus or minus radical 5. There you go. You can write it in a plus 5 form, or you can break it down. You got the plus, you got the minus. I think on the take home I have you break it down. But you know something, if you gave me with the plus, let's just break it down. Okay, another thing is a latus rectum, which has to do with the width of a line segment going through the focus and perpendicular rather to the transverse axis. Okay, so it'll be here and here, and formula is 2b squared over a. Put the numbers in, you get lattice rectum length is 1. So basically, if you look from here to here, I mean, hopefully you can tell that that looks like about 1 unit wide, and the total here across about 1 unit wide. So that makes perfect sense. Okay, asymptotes. For this type of an hyperbola, well, what we're going to use is point slope form. So the line, or the point that the lines, which are the asymptotes, go through is negative 2, 1. So therefore x plus 2 here and y minus 1 there. That's your h and your k. And then the slope. And you know, you can sort of like look at your picture here. It's all right, change in y over change in x. And the change in y is the value of a. And the change in x is the value of b. So that's why for this type, a type 2, where it's higher than it is wide, is the form plus or minus a over b would be the slope. You write it down, there you go. And you plot them. So, you know, and when you plot these, don't go crazy and put this into y equals mx plus b form. That's not an efficient way. You just start at negative 2, 1, which is the center of the ellipse, center of the hyperbola, and that's of course the intersection point of the asymptotes. And then you count. You're going over 2, over 1 rather, up 2, and that's how you do it. Eccentricity, c over a. Eccentricity for hyperbola, as you saw from that chart we did earlier, supposed to be bigger than 1, and it is, because this is about 2.236. Divide by 2, you get this value bigger than 1. Everybody's happy. Okay, so here's your graph. Should look something like that. I mean, I did it in colors. It's important to draw in the fundamental rectangle. Okay, that helps us a lot, because then if you connect the opposite vertices, right, draw a line through the diagonal, you get the asymptotes. That makes life easy. Okay, so the fundamental rectangle in this case has height 2a and it has width 2b. All right, and we're going to see that that's really the easiest way to help us get a reasonable sketch. Okay, so that's what you got to do. All right, let's look at a second example. Then I repeat, this was a type 1 because the transverse axis is vertical, and this is actually called the conjugate axis. We don't really label it, but that's what it is. Okay, so go to example number 2. Example number 2, analyzing graph, and you've got the same type of equation again. So we're going to notice, got x squareds and y squareds. It's got a minus in between, it's going to be a hyperbola. And again, I know it's a type 1, we'll get there later on. So you go through this process, okay? 9x squared minus 18x plus box, and then minus y squared minus 8y, and we've got to be very careful with the SIGNs as we've discussed in the past, so we'll go through this again. And the rule is you take, half the coefficient here if it's a 1 in front of the y squared and square it, so that's a 16. So we're adding a negative 16 to both sides, and over here, half of negative 2 to negative 1 squared is 1. 9 times 1 is 9. We're adding a 9 to both sides. You get an 81. Yes, this is a cooked problem. I picked the numbers so they work out nicely. Okay? And once again, standard form means you want a y here, a 1 here rather. So I'm going to divide each of these terms by 81, and that's how I get my standard form. Okay? And then the center is 1 comma 4, right? 1 is your h and k is your negative 4. And a squared goes with the positive terms. A squared is 9, a is 3, b squared is 81, b is 9. Let's see if I did this right. A squared is 9, b squared is 81. 9 and 81 is 90, so square root of 90. Let's say 90 would be 9 times 10. 9 is a perfect square, so 3 radical 10. Okay? And radical 10 is 3 and change, right? 126 or something. I probably wrote it down someplace. All right, so 3 times that is going to be 9 and change. So you can see, you go from the center, and we're counting out 9 units either direction to get our foci. Now, don't be tripped up. In order to make the diagram a little less dense, I counted by 2's. So you're going from a center, which is 1, negative 4, out to 3 radical 10 comma negative 4. Okay, so we've done this in the past. Vertices, in this case, the transverse axis is horizontal. This is a type 1. Okay, so if our center is 1, negative 4, a is a 3, we're counting 3 units to the right and from the center and 3 units to the left, and that gives us vertices of 4, negative 4, and negative 2, negative 4, as I labeled here. I didn't want to put the coordinates in the diagram because I think it would make it too cluttered. Did I do that here? No, I just put in the letters. Now, if I had a little more room, if I was doing this on the chalkboard, I'd probably put in the actual coordinates. But you're at home and you're sitting here, and hopefully you can print this out. You can write it in. I think that would probably be a good way to go. You write it in, you have it for future reference. And since we're moving horizontally to get the foci, the y's are the same. It's 1 plus or minus 3 radical 10. That's how I wrote it out. And then you go through the usual stuff. You got your latus rectum is 54, which is huge, right? It means you're starting here, you're counting up 27 and half and down 27. I didn't want to picture that. The diagram would just be too nasty to view. So we'll just take that under advisement. Asymptotes, we've done it before. Y minus k, x minus h, plus or minus. And in this case, because it's a type 1 ellipse, okay, you're looking at this now, and you're thinking the change in x is an a, and the change in y is a b. So that's why it's b over a. You just got to be a little careful. So keep in mind it's b over a in a type 1 ellipse, whereas in a type 2 ellipse, it's a over b. Okay, so this is not a typo. It's based on the orientation of the axes. Okay, and that's pretty much about it. And again, you get the idea of the fundamental rectangle. Okay, the width of the rectangle is 2a, and the height in this case is 2b, and that's how I know how large to make it. And I put little dots here. Those would be the what are they? I'm just counting up and down from the center, counting up how many units am I counting up? I guess I'm counting up nine units. Each box is 2, so 2, 4, 6, 8, 9 units up and 9 units down to help get the size of my fundamental rectangle. And then I extend the diagonals, right? I draw through the opposite vertices, opposite corners, and I get my asymptotes. It makes a nice graph, and then I know it goes through here, vertex, and you can really make a nice curve. So the use of the asymptotes, the fundamental rectangle are really important. Okay, so that's pretty much about it. We did 2 videos on the theory. I did 2 on actually graphing these things, and maybe if you're like me, when I was in school a few years ago, I would look at the examples, I go back to the theory, and I say, oh, is that why that's why that was, or is that what that meant? Okay, so that's the way it works, and I guess we're pretty much done with the conics. Now I might be doing something on rotation of axes. I think that's section 11.5. I haven't decided. But after that we go into parametrics, and that will be the content of chapter 11. So it will be the conic sections. We didn't do circles, but you know, we've done that in the past. So it's really circles, parabolas, ellipses, hyperbolas. If we do the rotation of axes and in parametrics, that would be the content of what I would call the next exam. But the next exam really is composed of the take-homes. You can have a take-home with parabolas. You got a due date on Blackboard. Ellipses, you got a due date a couple days later on Blackboard, and you got the hyperbola problem set take-home a couple days later due on Blackboard. Check the dates. Use the blank answer sheets I provide. This way it's easy for me to grade. I'm looking at the boxes and give you a nice grid to work with. Okay, as I said, I'm not sure yet whether we're going to do rotation of axes. We'll see. Okay, so have a good day. Hope this finds you well. Be well.